Hi, everyone. So today we're going to go over the remaining section or the remaining couple of sections for topic five. And this actually covers a lot of the topics that we discussed in time value of money and loans and bonds. Like this is sort of the culmination of everything coming together about what you learned in time value of money, what you learned in bonds, what you learned about coupons, what you learned about loans and bonds, and all of these different concepts coming together to really assess the effectiveness of a portfolio to match assets and liabilities and to discover what duration means because a lot of the concepts are finally coming together here. So we'll start off with a couple of terms. So MACD, Macaulay duration, refers to the weighted average time of all the future cash flows. So the individual weights are the proportion of the present value that time accounts for out of the sum of all of the present values of the future cash flows. So the weights, you can think of them as sort of building blocks for figuring out on average what is the average time that I'm getting a specific payment at. So you can see we're adding up all of the weights, the sum product of the weights and the times, and this will always be between 0 and n because you can think of this as sort of an average time, a weighted average time of when the payments will occur relatively. So this doesn't take into account the actual value of the cash flows, just relatively the amount when the amounts relative to the total payment will actually get paid out. So for a single cash flow, the Macaulay duration will just equal the time of when the cash flow occurs because 100% of the entire cash flow is just from that one time. If there was 50% from time two, if there was 25% from another time, then we will take the weighted average of that. And the weights again come from the present value of the cash flow. So let's just go through an example like what this actually means. So the first step you would do is you would first convert all of the cash flows to present value. So discount everything, all the future cash payments, discount that by multiply by b however many times you want to get to the present. That's the first step. The second step is to see what proportion of each present value is that specific cash flow. What proportion of the total present value is that specific cash flow's present value? So you would do the present value of that specific cash flow divided by the total present value. And so that would give you the weight for, let's say, time one. And then you would do the same thing for the other future cash flows. And this will get you to a time between 0 and the last payment date, right? The 0 and n, the number of payments, the 0 and the reason that it's going to give you between 0 and n because it can't be greater than the last period or the last term where you make the payment. And so MACD, there's also this notation of derivative, so you can remember that it's the negative derivative of the price with respect to the force of interest over the price at the force of interest. And the first step that you would do in it, if you want to calculate this way, is just set up your entire present value formula in the way that you would, in the way that, assuming that you have force of interest. So you would do the price at time one times e to the negative force of interest times t1. And then you would add up all of those to get to the present, value. And that would be your p of your force of interest. Then you would take the derivative of that, and then you would divide that by the value that you're at, the price of that force of interest that you are at. And just remember that force of interest is the natural log of I. And then these are some formulas that it's helpful to know. Won't go through the derivation here, but you can go through like the steps and how to calculate MACD, and that's how you. And then basically just simplifies down to these, and that's how you actually know that these formulas work. So MACD we have formulas for MACD annuity immediate, MACD of a bond sold at par, MACD for cash flow that increases geometrically by K indefinitely. So these are some formulas that if you just see, if you just see calculate the MACD and you immediately recognize that it's one of these three, then you can just simply jump to this formula without having to calculate everything else. And then a couple other things I want to mention here is that par value versus at par are different terminologies. So these are common terminologies that may come up in questions, and we just want to understand that these are like two completely different um, these mean two completely different things. So par value is just the redemption, or par value is what you refer to as to calculate when you're calculating the coupons. And at par means when the price is actually equal to the par value. These are two different terminologies. Again, sounds pretty very similar, but we just want to make sure that we make a distinction between these two. And then mod D is equal to mag D times V, just another relationship. And here you can see the derivative relationship as well. And then as price increases, the yield or the interest rate decreases to achieve a similar future value. And this makes sense because as the price increases, you're going to need a lower interest rate to you don't need to accumulate as much in order to get to a certain value at the end of your term structure, the payment structure. This is a first order modified approximation if you want to calculate the impact of a change in interest rate. So let's say you know what the mod D is, you know of your payments, you know what the original interest rate was, you know what the original price was at the interest rate. Now you want to change the interest rate and you want to get an approximation for how that's going to change the actual price. So you can use this formula. We won't go through the derivation here, but this is something that should be memorized. And then another way of also approximating this is through the Macaulay approximation. And you can see the formula here where you can calculate the new price. Again, same thing as this, or similar to this, by using the original price and the original interest rate and the new interest rate. Passage in time refers to how can we know how the Macaulay duration changes between two time periods where the two time periods in those two time periods the cash flows are unchanged. So this is a formula that you can use where you're going from, let's say, time period 0 to time period 1, assuming that the cash flows have not been changed, or assuming that you haven't paid, but the number of payments and the amount of payments have not changed. So if you're going from, let's say, time period 0, and let's say the first payment starts at time period 1, you're starting at time period 0, you've calculated your Macaulay duration, then you're going to immediately before time period 1, and note that time period 1 is when the Macaulay duration, the first payment happens. Because you've not changed your number of payments, because you're going immediately before time period 1, because you're not changing the number of payments, because you're not changing the amount, the total amount total amount of cash flows that you're paying in the future, you can use this formula. You can use T2 minus T1. You can simply use the change in the actual duration on which you moved to calculate what your new Macaulay duration would be. And so this is a formula where you can use where, if you have some question where you want to just quickly determine what's the change in Macaulay duration if I go from this period to this period without assuming that the cash flows are unchanged and assuming that nothing extra has been paid when I move from this time period A to time period B. And note that if it does change, or if the number of payments or the number of cash flows does change, then you have to recalculate the Macaulay duration using the things that we talked about. Okay, so let's go to the next slide here. And so for mod D, for modified duration, this is the formula that you would use. Essentially the same thing, except you're just adding a factor of B. Portfolio duration, so we talked about duration, we talked about what Macaulay duration means. Now, portfolio duration is, you can think of it as the weighted average of the duration of each individual assets. And again, the weights come from the prices and the times are the duration. So in the previous duration example, or the duration definition that we went through, the weights were the proportion of the present value that your payment present value accounts for. And so in this case, the weights come from the prices and the times are the duration. So again, it's much easier to see this through an example. So the more that you actually get used to this, but it's essentially the same concept as going through your weights, figuring out what the weights are for the price for each individual asset, and then weighting each asset in proportion to the total price, and the times are the individual. And then you multiply the weights by the times. And then when the coupon rate equals the interest rate, you can use this formula for bonds. I think this already covered here. So this is just a formula. So the coupon rate equals the interest rate. So if it's at par, right? So if it's at par, so at par means that the price equals the redemption amount, or the par value. The price equals the par value. and FR equals CI. So if you don't know what that means, it's better to watch the video, but FR equals CI essentially means that the expected coupon payment equals the actual coupon payment. And then we have this notion of convexity. Convexity, you can think of this as just another metric to improve the approximation of price. So previously we approximated price using these two formulas. You can think of convexity as another idea, another concept created to really improve this approximation of price. And it's really trying to determine the curvature of 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 this curve, of this price curve. Because if we can understand that better, then we can better approximate the price. So you can see the formula for mod C. What you want to do, again, as we previously mentioned, is really put your present value in terms of I. So if you have these future cash payments, you want to discount that by 1 over 1 plus I to get to the present value. And if we make this into, if we just visualize this, right? This is the sum of t times t plus 1, v to the t plus 2 times the cash flow of t over the, so that's the second derivative. And then present value obviously is just the cash flow at time t discounting by v, the number of payments to get to 0. And then mag c, so we have mod c, and then mag c, you can see the formulas over here as well. And then you want to realize that you can make these shortcuts by understanding which are like annuities, which are common things that you've seen before that you can just use your TVM keys on your calculator. So this is just an annuity. You can use your TVM keys and so on. And then this is a very important relationship that we need to understand. If we have two of these, mod C, max C, and mag D, we can solve for the other one pretty easily. So mod C equals V squared times mag C plus mag D. And a lot of questions I've actually seen where you're able to easily get like two of these, and then it's asking for like the third one. And just by using this equation, you can actually get that value. Portfolio convexity is, again, same concept as portfolio duration, and it's the weighted average of each asset convexity. Instead of the weighted average of each asset duration, it's the weighted average of each asset convexity. And the weights, like the duration, comes from the proportion present value of each cash flow. And then Reddington immunization, you can think of Reddington immunization. So what is it even immunizing against? Well, it's immunizing against these small interest rate changes. So it's a way for us to protect the portfolio against small changes in interest rate. As we know about this, as price increases, the yield rate decreases. And this is actually a concept that in bonds and loans, whenever you're working with these problems with like the yield curves, is a very important concept to really fully internalize and understand. So protection against changing interest rate. That's like really just what you need to know about the purpose of Reddington immunization. Now, what are the three main things you need to make sure about this? Well, the present value of the asset has to equal the present value of the liability. So what you have to do is you have to discount all of your asset cash flows, discount all of your liability cash flows, and have to make sure that they're equivalent. So what you'll get is you'll get an equation with this, typically with two unknowns. And then the second equation, the duration of the asset has to equal to the duration of the liability. So first, calculate the duration in terms of x and y, calculate the duration of the liability, and those two have to be equal. Now, what you'll see is from the first two sets of principles, the present value being equal to each other of the two assets and liabilities, and the duration being equal to each other of the assets and liabilities, you'll see that you'll get a system of two different equations. And so you'll be able to calculate x, and you'll be able to calculate y, the prices. And now, just to make sure that this actually satisfies the Reddington immunization, we have this third criteria where the convexity of the asset is greater than the convexity of the liability. So what you'll do is you'll take the second derivative of both the liability of the asset function with respect to the interest rate and the liability function with respect to the interest rate, and you'll see if the convexity of the asset is greater than the convexity of the liability. And what this means is if that's the case, then we know that the surplus is always going to increase despite small changes in the interest rate. So if liability ever exceeds the asset price, then we know that the liability will be greater than the asset. The surplus will be less than 0. That fails the Reddington immunization process. And now full immunization, this is another immunization technique. And you can test for full immunization first, and it might be actually easier to test for full immunization first. If you know that something is fully immunized, if you know if portfolio is fully immunized, then you already know that this satisfies Reddington immunization. So, and the entire purpose of this, is to immunize a single liability for any rate change. So while Reddington immunization protects portfolios against small interest rate changes, this protects portfolios against any interest rate changes. So that's sort of the difference there. And again, this is more again strict in terms of like what it actually requires. But you can think of if any portfolio satisfies full immunization, then it also satisfies Reddington immunization. The two principles or the two requirements are the same from Reddington immunization. The only difference is in the third part where you must have at least one cash flow between and after the liability. So you can think of the liability being sandwiched between two different assets. And so whenever you see that, and again, they don't have to be like directly like plus or minus one time period apart. They just have to be like it could be like plus or minus two or plus or minus three. There just needs to be an asset before the liability and asset after the liability. So if there's an asset at the very end and there's no asset or liability at the very end, and there's no asset that's after it, then that wouldn't be considered fully immunized, and that would fail this full immunization test. And then we can see the general concept. So that I included this just so we can see the general concept of prices and yields and the asset and liability curve. So here we see in this curve that asset is always greater than the liability. And so we know that the surplus is always going to be greater than zero, passing the full immunization test. And meeting full immunization implies full Bennington is achieved. We talked about this, and it's very easy. And like the thing I want to emphasize, it's very easy to check that it's fully immunized, right? You just have to check the structure of the payments if all of the liabilities are sandwiched between assets, and if that's the case, then you already know that it's Reddington immunized. So that's one of the key tricks for this. If you want to see something's Reddington immunized, just check first. Just check if it's fully immunized. If it is, then you don't have to do anything else. And then okay, so that's about it. And then we have this concept of exact matching. So the only assumption in exact matching, is that the cash flows are fixed. So in the previous two Reddington immunization examples, we gave these different assumptions. Those assumptions were, let me go back to the assumptions. The assumptions were that we have a flat yield curve. So basically, spot rates like being different are not a thing. We have parallel shifts in the yield curve. So again, it's constant for every single time period, and we have fixed cash flows. The cash flows don't change. The only assumption that we're taking from that onto this is that the cash flows are fixed. The cash flows are fixed. So you can have spot rates. You can have spot rates, different spot rates. And here, what we really want to get at is the amount and timing of the liabilities cash flows match that of the assets. So what we're doing here is we're taking, and if you don't want to draw this table, it's fine. If you can just draw like a timeline of a graph where you're matching the liability with the asset itself. So you want to start with the asset with the longest duration, longest time period, and you want to start with the highest liability or the basically the liability at the very end, and you want to match that first. So if it's depending on how many like bonds you want to buy in order to match that amount, and the leftover, let's say you have additional coupons, the leftover would get transferred to the next asset liability asset liability entity that you want to equalize or equate. And so do not discount when matching, just match the individual time period. So we're just matching the individual time periods, right? So if at time period one, I have a liability of 1,000, our asset at time period one also has to be 1,000. And then how can we do that? We can do that by adjusting the number of bonds that we actually purchase to make that happen. And when we make that adjustment, we also have to be mindful that that actually causes changes to like the previous time period as well. So we have to account for that. And we can do that through like this. Again, there's many different ways you can do that. What I've found most useful is you do it via a time diagram, and you just check. And if it's 1,000, like for me, it's very easy to like lay out. Okay, this is from bond A, this is from bond B, this is from bond C. You can also use like this chart or graph if you want, if that's easier as well. So yeah, start with the liability with the longest duration, and then buy the asset that exactly matches that liability cash flow. So if you have a liability, let's say X with in the longest duration at time period 3, you want to buy the asset that first matches whatever the payment, whatever the amount is at time period 3. So again, if you have to purchase X number of bonds, you do that to match that amount. Taking, like, if it's a bond, you have to make sure that the coupon payment plus the actual redemption amount equals the value that of the liability. So, and again, this is better if you just do more practice problems. I just want to cover like the high level concept of this. So yeah, again, I just made this note that you really need to do the practice problems themselves to understand these different concepts. Just want to quickly go over this last section here where I have a duration example where you can see we have, oops, where we have these $40 annual coupon payments, and we have the 1,000 being the par value. You can see that how we actually calculate the Macaulay duration by first discounting each cash payment to the present value. And then the weights, you can see 40V over PV, 40V squared over PV. You can see the weights are just the proportion of the present value over the total of the total present value. And so those are the weights, and then we're just multiplying those individual weights by the actual time in which the cash payment actually occurs. So then when we sort of combine all of that together, we get this large formula, the computation here where we're, and you can notice like the 1, 2, 3, 4, 5, that's like the unit increasing annuity, and then the 40V, 40V squared, 40V cubed, 40V4, that also forms another sequence as well. So you can use that. You can use an increasing annuity, 40 IA5 3%, representing the numerator part, and then obviously there's this an end portion, 5 times 1,000 b to the fifth, which really doesn't isn't aligned with the rest of the sequence. So then you could just add on to that. You could add on to that unit increasing annuity. You could just add on the 5,000 v5, and then the denominator is just your typical present value. How do you calculate the present value of a typical bond? And so when we generalize this to any sort of any bond, we can see that the numerator is always going to have the coupon payments. So that's FR times the a unit increasing annuity. So the unit increasing annuity is referring to the 1, 2, 3, 4, 5, and then we're multiplying by 40 because of 40V, 40V squared, 40V cubed, and so on. And then plus CNV to the N, which refers to sort of that last term that doesn't really fall into the the sequence itself. And then the denominator is just your typical present value of a bond. And you can use your TVM keys on your calculator to actually compute this as well. So that's going to make your life a lot easier. And then I also want to mention another thing is when you have different equations, so let's say you want to find the overall yield rate, but your cash flows are like, let's say 3 or 4 or more than 2. They're more than 2. And so if it's only 2, you just have to solve like a quadratic formula, right? So if it's only 2, then it's like let's say like your two cash flow payments are like 500 and like 600. That's 500 VV plus 600 V squared equals your present value. That's not too bad. That's just your that is. And if you want to calculate the yield rate, like you just solve the quadratic formula. But if it's now 3, 4, or 5, I mean that's like a 5-degree, 6-degree polynomial if it's 6 payments that you have to solve, which is very time consuming, probably not even possible for you to do by hand. So for those types of questions where you get to a point and you have to calculate the yield rate where you're working with like 6-degree polynomials, you're probably better off using your calculator. And what you can do there is you can go to the cash flow keys, enter in CF0, then you can hit enter and then hit the down arrow, and then you'll go into, okay, how long do you want this for? So you'll set like f equal to 1, or f equal to 2 if you want that to occur 2 times. And then you just lay out the entire sequence there, and then you just hit CPT IRR to make sure that or to get the yield rate. And you really want to make sure that when you hit these keys, you want to clear them as well. So that's another important point I wanted to make is like when you're doing a lot of these calculations, it's very easy to just lose track of like, okay, did I put this here? Did I put this there or whatnot? So you really want to just make sure that you clear your work in the beginning before you start a new problem. So yeah, that's all I wanted to mention, some extra tips and tricks. So yeah, this is essentially all of the rest of the topics covered in this section. I think it's I think like I mentioned in the beginning, like this really encompasses the duration, like bonds, time level of money, loans, like all of the concepts and individual things you learned throughout the other remaining sections. Like this really takes it and just integrates everything together. So, and I think like a majority of the questions in the exam will be focused on like this exact matching and immunization and really portfolio types of questions because contain integrated they integrate multiple concepts together. So like just from this Reddington immunization to know what this Reddington immunization is and to like make a portfolio immunized, you have to know how to calculate present value. If it's a bond question, have to know about bonds. Yeah, and obviously that requires knowing about time value of money. So you're really just integrating a lot of these different concepts together when you're asking these questions. So you're more likely to see these types of questions: full immunization, exact matching, things with things with bonds and coupons in these types of questions because just they test a lot more and they're great questions for testing your understanding on a wide variety of topics. So please make note of this how the importance and weight of this section and these topics. So that's all. Thank you for listening, and then I'll see you in the next video.